Welcome everybody. It's a pleasure for me to introduce Daniel Hammer. Daniel has been working as a mineralogist, working in the US. He's been working recently with Hazen, one of the team working on the so-called mineral evolution in our ecology, which is a new way to present to understand the formation of the mineral diversity. Daniel contacted us recently because he's been aware of his opening position as a full professor in the museum for next year. And so he was interested and very happy to share his results in science and discuss with us about the opportunity to apply for this position. So of course it's a purely informal talk today. We're not going to discuss about this opening. It's more like an introduction of his work. So please, Daniel, we can go ahead for say 45, 50 minutes or so.
All right, thanks very much, Mathieu. Should I go ahead and start now?
Yes, you can go, Daniel.
All right. Well, thank you everyone for being here. It's great to be able to give a seminar in Paris, even though I'm not in Paris. That's the sad part. I would love to actually be in Paris. I've been there twice, and it's a beautiful city. I am, as Mathieu mentioned, I'm a mineralogist at Southern Illinois University in the United States. And I've done a lot of work, both experimental and on the data science side. I've done a lot of work on crystallization of minerals from aqueous fluids and also at high pressures. So I've done a lot of high pressure experimentation. But what I'm going to show you today is mostly the data science side, trying to trace the Earth's past by using these really large mineral data sets where we've agglomerated a bunch of data from just from mineral occurrences all over the world, simply knowing how many occurrences there are, where they are, what their geologic age distribution is like. And we can use this actually to learn quite a lot about the Earth. In much the same way that in using traditional methods, we can learn a lot about the growth of minerals from particular locations, from nicely zoned crystals, just like the fluorite that you see on the screen. So before I get into the results, I want to acknowledge all the collaborators on these various projects that I've been working on, and there's a large number of them. When you're working out Earth's history and you have this much data, you need a lot of collaborators. And I'm very fortunate to have some of the best in the business. In particular, I want to point out Robert Downs. Bob Downs is a professor at University of Arizona, and he is responsible for one of the main data sets, one of the main profiles of minerals that we use in these studies. Of course, the ideas behind mineral evolution were launched about 15 years ago by my former postdoctoral supervisor, Robert Hazen. So he's pictured right there. Peter Fox established a lot of the data science methods that we are now using. And he was a wonderful collaborator for a long time. He very tragically passed away a couple of years ago, but I always make sure that I point out his contributions to what we're doing now and all of the ways that that will influence us moving forward. And also Shauna Morrison at the Carnegie Institution has been a key collaborator, along with the rest of the folks on the screen. So let me just give you a brief outline of what I'm going to talk about. First, I'll introduce you to the databases that we use. for these studies. Of course, you have to have very large data sets, and you have to have representative data sets in order to do this. So I'll show you where it is that we obtain that data. And then I'll kind of go through two main concepts and give you a cross-section of projects that I've been working on related to each one. The first one is mineral ecology, which just has to do with the distributions of minerals on Earth just now in a, right now as a snapshot in time. So I'll talk about the frequency distributions of minerals, network analysis, which is about the associations of minerals at particular locations, and I'll talk about other correlations and patterns that we're using these mineral databases for. And then second, I will talk some about mineral evolution, which is the study of how Earth's mineralogy has evolved over geologic history. And we're even branching out now and looking at how the mineralogy of other planetary bodies might have changed over history. So I'll talk some about changes in mineral chemistry over time. We'll look at some consequences of oxidation, the Great Oxidation Event, and some new things that I'm planning. So I did not know if everyone at the talk was going to be in the mineral sciences. So I just included a brief slide to remind everybody what the definition of a mineral actually is. So when I use the word mineral in this presentation, what I'm talking about is a solid, naturally occurring, and crystalline substance. Has to have all of those characteristics. That is characterized by a unique combination of both a chemical composition, meaning a chemical formula that we can easily write down, and a particular atomic structure. So of course, one of the classic examples to show that you can have these different combinations is we have pure carbon both in the form of graphite, where the carbon atoms form these nice sheets, gives it a layered structure, and makes it very soft and lubricating. And then, of course, diamond, which bonds in a different fashion and creates a three-dimensional interlocking network of carbon atoms. And that, of course, creates the mineral diamond, which, as you probably all know, has vastly different properties than graphite does. So when we talk about a mineral species, we mean one of these unique combinations where no other substance has that particular combination of chemical composition and structure. So where do we get all of this mineral data? One of the key places that we get it is at this RUF website, ruf.info, which is housed at the University of Arizona. This is the one that Robert Downs created. And there's a website for it. You can go to it for free. Perhaps even a few of you already use it. And what you'll find there is this lovely menu, this nice listing of all mineral species with their official IMA names in alphabetical order. So you can click on any one of them, and then you see information about that mineral off to the right-hand side of the screen. There are over, I believe actually over 5,900 species now that are listed on this website. Another really useful feature is that you can search by chemistry. So if you're looking for minerals that contain a particular element or a particular combination of elements, you can click those buttons down here on this periodic table, and it will automatically filter the list just in a couple of seconds. You can do this online over the internet, and it will narrow it down to all of the mineral species that have that particular chemistry. And also for our purposes, for looking at mineral evolution, one of the crucial things is that they have incorporated this relatively new, this is just over the past several years, mineral evolution database, the so-called MED, and that contains now over 120,000 mineral locality age triplets of data points. And so what we mean by that is that a particular mineral occurs at a particular location, and it has been dated with reasonable accuracy, using standard methods, using radiometric methods, or whatever it may be, to have formed at a particular geologic age. So that's also something that we take advantage of. Oh, yeah, did someone have a question? By the way, if you have questions in the middle of the talk, just please feel free to raise your hand and speak up, and I'm happy to answer those as we go along. Did anyone have a question? No. Okay. Okay, so we'll continue on here. So another key place that we get data, and this is for the most part where we get our locality data. Where do all of these minerals occur in the world? Well, there is a website, mindat.org. Again, this is maybe one that some of you have used before. It's a marvelous online database. It's, again, searchable. You can search for mineral species. You can search for location names. And there are over 275,000 locations on Earth that are described in this database, and well over 1 million now, 1 million and counting, mineral locality pairs, meaning, of course, a mineral occurring at a particular place. So a lot of that data from MINDAT has now been incorporated into the mineral evolution database, and we are adding geologic ages to a lot of those mineral locality pairs. So this is a very large database. Now, of course, I should mention, a lot of this data relies on, not just professionals at museums and universities and so forth, but also collectors to submit data on what minerals they have found at particular locations. You cannot build a database this big unless you draw from many, many different sources. And so at MINDAT, which is run by Jolie and Ralph, they have a procedure for kind of double checking the accuracy and vetting the information that is uploaded to MINDAT to ensure that it's as accurate as possible. They do not just allow anyone to submit and then it stays on the website permanently. And we've, of course, been working with him to ensure that these procedures are useful in the long term for keeping the data set robust. Okay. So let's talk a little bit now about mineral ecology. And mineral ecology is really just the concept that surely there are some kind of patterns or large scale patterns that we can notice about the distribution of mineral species on Earth. And of course, that makes sense at a local scale. Whenever you have a particular kind of deposit, you're going to see particular kinds of minerals because they formed in a similar way. But we can do the same thing on a global scale, and we can even see patterns in global data sets that we would not necessarily see just looking at individual localities or deposits. So one of the first things that happened during our studies is that we tried to work out, is there a large-scale distribution in just, the number of times that different mineral species occur on Earth? And it turns out that there is. If you look at the species frequency distribution of minerals, we can use these data sets, for example, these 275,000 different localities that are on MINDAT, and you can use them to tally up, well, how often does each mineral occur? And as it turns out, the result is really stunning. The result is that the over 5,800 known mineral species that we have at this point actually adopt exactly the same statistical distribution as words in a book. Or turns out it's also the same as biomass in an ecosystem. And what that distribution is you have just a few minerals that are very, very common, that occur all over the world, but then most mineral species are actually rare. And if you think about that, that kind of rings true. You've got quartz and the feldspars and the micas and some minerals that everybody has heard of because they occur all over the world. Okay, they're practically everywhere. But that only accounts for a handful. You can, off the top of your head, you can probably come up with 10, 20 or so, but there's nearly 6,000 mineral species now. Most of those occur in only 1 or 2 places in the world. Okay, and it turns out this is exactly the way that words in a book appear. Okay, if you think about, opening up a book to a random page and picking out a random word, what word are you likely to see if you go through that totally random process? Well, some of the words that you're most likely to see are a, and, the, is, at least in English. In French, perhaps you're likely to see et, and other things. So those words are very, very, very common. Okay, you see at least some of those words in practically every sentence. But all of the rest of the words that an author is using to describe something are normally pretty rare. Okay, the word bookshelf, for example, is, a well-known word, but it's used very rarely. We don't use it that often. And it's actually those rare words that define the authorship of the book. And in fact, linguists do these statistical analyses. They analyze the word frequency distributions in a book. And from those distributions, you can actually figure out who the author was. And linguists have discovered the authors of unsigned manuscripts by going through this process. And not only that, but you can also use the author's total vocabulary. You can use the statistics to project the total vocabulary and determine how many total words that author actually knows, because they follow such a regular distribution. So minerals do the same thing. So here I'm showing you a graph on the vertical axis is the number of minerals that are found in a particular locality. And then on the horizontal axis is the number of localities. Okay, so in other words, the way to read this, and this is something that was published in Mathematical Geoscience several years back, the way to read this is that there are over 1,000 minerals shown in this first bar here that occur at only one location on Earth. There are about 600 different mineral species that occur at only 2 locations on Earth, and so on and so forth. So again, you see this pattern where a lot of minerals are rare. They're occurring at only one location. And then the distribution trails off, and there's only a few minerals that are found at many locations. And this type of distribution, by the way, is referred to as the large number of rare events distribution. And that's something that's well known by statisticians, and that's the way that you can describe these frequency distributions. So another way to look at it, and this is something that biologists actually do, and we're now starting to do it as mineralogists, is if you count up the total number of biological species, or in this case, mineral species that we know about, and we tally that total number of unique species on the vertical axis, as we are counting at different locations, as we make different observations of mineral species, and those just individual observations are counted along the horizontal axis, then here's what that looks like. In the very beginning of the process, as we're counting up those unique approved mineral species, what we find is that in the early going, we are discovering new species very rapidly, because most of the new observations that we make are giving us new species, because at the very beginning of the process, we don't know about anything. So that curve climbs very rapidly. But as you continue going to another location, and you start noticing, okay, here's a mineral at this location, here's a mineral at this location, you start overlapping, you start repeating observations more and more frequently, and therefore you're discovering new mineral species less frequently. Okay, so that process slows down. If we look at this process even just 9 or 10 years ago, we knew of only 4,800 mineral species, okay, and now we're up to about 6,000. So that's where the data were when we did download it at this particular time in February of 2014. But now we have even more species. But of course, those new discoveries taper off as we move into the future. This is what it looked like in February of this year, just to compare, do a direct comparison of 9 years later. And now, again, we're closing in on 6,000 species. So knowing exactly what this distribution is and how it evolves as you make observations, we can actually use this to predict that there should be in the neighborhood of 6,400 mineral species that exist on Earth today. Now, one caveat about this, though, and that is that this technique, this statistical technique, assumes that we are making mineral observations at a similar rate through time and that we're using the same techniques that we've always been using. But as anybody who is in the scientific business knows, we're constantly opening up new avenues of research. We're constantly getting new instruments that give us new capabilities, and that changes the game. Okay, that changes the statistics. So you have to take that into account. So when we do that, when we take these other factors into account and use a more comprehensive Bayesian method for doing this estimate, it actually gives us about 9,300, okay, over 9,000 different mineral species that we believe exist on the Earth right now. So that's pretty amazing to think about. That means we've discovered, maybe less than 2/3 of the total mineral kingdom that is out there, even as many discoveries as we have made. We believe that there are in the neighborhood of 3,000 mineral species that are on Earth, that exist somewhere, but are just still undiscovered. So where are all of them? Well, I embarked on a mission to at least find, a few of the ones that have some particular chemistry. So I launched back in December of 2015. I launched this project called the Carbon Mineral Challenge, and maybe some of you have heard of it before. But what we tried to do is initiate this worldwide effort to, not just let these minerals fall into our laps by happenstance, but we wanted to know, can we actually make some predictions about what these mineral species are? Can we make predictions about the rest of the mineral kingdom and then do a specific search for those minerals and see if they actually exist? See how many of our predictions are correct. So I was very excited to do this. I felt like this made mineralogy in a sense more of a predictive, not just purely observational, but a predictive and theoretical plus observational science. So we made all of these predictions. We actually published a paper predicting many different new carbon-bearing minerals. We focused on carbon because it's such an important element at the surface of the Earth. Life is based on it. Carbonate rocks, of course, are based on carbon-bearing minerals. So we launched this effort and we advertised it all over the world. I spoke with and messaged with both amateur collectors and professionals at museums, professionals at universities, at mineral societies around the world, mineral journals. And we got the word out and we tried to motivate as many people as we could to look in their collections and see if they could find any of these so-called missing carbon minerals. So this project ran up through 2019. It's now been over for a few years and I'm focusing on some other things. But as it turns out, as a whole, as a community, we actually did end up finding 32 new carbon-bearing mineral species during this time. And you can see all of them, by the way. They are all listed, and there's kind of a profile for all of them at this website that's listed down here, mineralchallenge.net. So you can take a look at that to find out more about the project. So how did we go about? Now, of course, we published a paper on this. Bob Hazen and myself and a couple of others published a paper predicting these new minerals. How do you go about predicting a new mineral? Well, we used a few different strategies. And just to show you one of these strategies, one thing that we can do is, of course, look at minerals that already exist, and we can come up with reasonable analogs. So for example, here's the mineral parasite cerium, and you can see here's its formula right here. It's a calcium cerium carbonate. Well, we know that the rare earths substitute for each other all the time. Okay, the rare earth metals are always substituting for each other. And in fact, in any given rare earth mineral, you normally have a mix. You normally have a distribution of different rare earth metals that is often dominated by just one or two of those metals. So it stands to reason that if parasite cerium exists, if we simply substitute that with another rare earth metal, its neighbor on the periodic table, lanthanum, it's reasonable to guess that we should also have that mineral existing in some other location that just has a slightly different distribution of rare earth metals. And so we predicted, one of the specific predictions that we made was that this and a handful of other minerals that contain these rare earths should exist in some deposit somewhere. And as it turns out, it was real. It was verified. We predicted parasite lanthanum. And indeed, that is one of the minerals that was found by a team during the challenge. So here's an actual photograph of parasite lanthanum, and I believe it was somewhere in Europe. I don't remember exactly where, but is where parasite lanthanum was found. So we made all of these predictions. We conducted this challenge for about 4 years. And what did we get? Well, here is a graph. I'm just kind of showing you the overall results. Here is a graph starting in 2018 and running up, 2008. And running up through 2018, charting the fraction of new minerals that were approved by the International Mineralogical Association that do contain carbon. So here is a graph of them, and the years of the challenge are shown right here, and then I'm showing, many preceding years just so that we can compare. And I did just a brief analysis. It doesn't look from the graph like it's all that dramatic of a change, the number of carbon minerals that were found, but of course we had some extra people working on it. And as it turns out, the running average prior to the carbon mineral challenge was 3.6% of minerals found contained carbon. And then during the time of the challenge, that increased to 5%. And as it turns out, that increase was, I did a two-tailed z-test just to see, like, is this statistically different, or was there an actual increase, or is this just happenstance? And it turns out the test says that yes, it is a significant increase, but only just so. It was significant at the point at a p-value of 0.026. So did the carbon mineral challenge make a difference? I think perhaps it did. I don't think that we can say that with certainty. I did this statistical test, seems to indicate that it made some difference, but I think we probably have to make a similar effort for additional years in order to really be sure of the robustness of that result. I published the results, by the way, of the carbon mineral challenge in the Australian Journal of Mineralogy just a few years ago, right when the challenge ended. So you can also take a look at that if you're curious. Okay, so we have all of this data on the distribution of minerals. Another really useful thing that we can do with this data is we can analyze exactly the quantitatively the ways in which different minerals are associated with each other. And this is an effort called network analysis. Network analysis is already a well-established technique in the social sciences, studying networks of people. The intelligence services of the United States, of France, of probably many other countries as well, use network analysis to track networks of terrorists, and try to hunt them down. So it's very widely applied, this social network analysis. And we are now, for the past several years, we have been using it in mineralogy to study the ways in which different minerals are associated with each other. And so this is just kind of an example of what one of these network diagrams would look like. And then each of these spots on the diagram represents a particular mineral species. So we can use now, as geoscientists, we can use this same formalism to explore patterns in mineral coexistence. And perhaps by studying the ways in which minerals coexist with each other and the frequencies with which they coexist, we might even be able to use that as a technique for finding new mineral species, for predicting new valuable deposits of critical metals that our society needs. So here's how this works. I'll show you a couple of examples of mineral network diagrams. So each spot on the diagram is called a node, And in all of these examples, they are going to represent a particular mineral species. Anytime that there is a link between two nodes, that indicates that those two different mineral species occur together somewhere on Earth at one of these, hundreds of thousands of localities that we have in our database. And then when you have many nodes interconnected together, that means that you have many minerals that co-occur at some location with a particular mineral species, and you have an entire network of coexisting minerals. And then I should also point out, we have, it's a very mathematical procedure. It's actually, it looks like we're just drawing dots and drawing lines, but we have a computer program draw these dots such that the more two minerals occur together, the closer they are together, the shorter the link between them. So you can actually look at the diagram, and the diagram, in a sense, is giving you a lot of quantitative information in addition to qualitative. You can actually see how often things occur together, and you can visually see clusters of different minerals that make up particular rock types. Okay, so here's an example of one of these. These are all of the common igneous rock-forming minerals that are plotted here on the same diagram, each one of these colored spots. And then each one of the gray lines that you see represents, again, how often any particular pair of minerals co-occur together. The size of the spots indicates just the frequency that the individual mineral occurs. How common is that individual mineral? The spacing corresponds again to the frequency of co-occurrence. And then we can also color the nodes or give them different shapes to denote different attributes. So for example, here we've broken them up into common mineralogical categories. Red indicates quartz and feldspars. Mafic minerals like the olivines and pyroxenes are mafic, so they're colored green. Yellow designates feldspathoids, and then blue designates other accessory minerals that don't fall into one of these categories. And you can see that they start to form clusters according to their category. The quartz and feldspars, for example, tend to group over here and tend to occur together. The feldspathoids tend to occur up here at the top of the diagram, and they most often occur together in rocks, ones that are silica undersaturated. So this network, as it turns out, for igneous rock-forming minerals is a very high-density network. And so there's various metrics that we can use. The density has to do with the numbers and lengths of the connections between those mineral nodes. And the more of those connections there are, the higher the density. And by the way, there are formulas that you can use to work out all of these metrics. They have a formal mathematical definition. So we can get a lot of information from these network diagrams and determine, all of the various ways that minerals are connected, that minerals can co-occur with each other on the Earth and in other environments. So here is a paper that we published. Our collaborator at Carnegie, Shauna Morrison, was the lead author on this, and then myself and several others were co-authors. And we plotted up all of these igneous minerals and did a very precise two-dimensional version of this network diagram. And when you plot this, out pops at you all of the major rock types that we know of on Earth. It's really pretty stunning, actually. So an olivine-rich basalt, for example, plots at this location in the diagram, all of these green ones. A granite plots right here over in a somewhat different location. Notice that there's no overlap in mineralogy between the basalt and the granite. A nepheline syenite plots right here. Notice it has a greater variety of minerals, but it does also overlap in its mineralogy with a granite. There's 3 minerals that are common between the granite and the nepheline syenite. So you can study the relationships between all of these minerals. You can correlate it with their thermodynamic properties. And all of a sudden, you essentially have all of igneous petrology, or at least all of the important aspects of igneous petrology sitting right in front of you in one diagram in a way where you can both visualize it and you can get a lot of quantitative information. So this has been a really powerful technique. And in fact, some of my collaborators have even used this technique to predict the locations of new minerals. When you see clusters of these minerals, it means there's a higher probability that if you find a few of the minerals, you're more likely to find another mineral at a particular location. So they actually did a statistical analysis looking for lithium deposits in the United States. Lithium is one of the new critical metals that we need. And they were able to correctly predict, they predicted the locations of lithium mineral species that might be economically important. And geologists went out to those locations to check to see if those minerals were there. And in most instances, they were. They made correct predictions about locations of new mineral deposits. So very exciting technique. So another thing that I have been working on, particularly recently, is analyzing the correlations of elements that co-occur together in minerals. So of course, we already know, qualitatively speaking, about patterns, of certain elements getting together in certain minerals. We know, for example, that some elements are lithophile, some are chalcophile, and so forth. So that governs a lot of their chemical behavior. But I wanted to do a very rigorous statistical analysis to quantify those tendencies. And so I asked myself, well, how often does a particular pair of elements occur together in minerals? Surely it's not all by chance, but does any particular pair occur more often than when you would expect by chance, less often than you would expect by chance? So you can pick a pair of elements from the periodic table. So for example, silver and sulfur, and say, well, how often do those occur together? And of course, in our data sets, we have all of the data that we need to answer these questions. We just look at these databases of mineral species, such as the one that we have at RUF, the RUF project, and we can tally up all of those species and find out, well, how many of them do have silver and sulfur occurring together? How many of them have silver occurring separately? How many have sulfur occurring separately? And so we can compare that and do a statistical analysis. And in particular, I was very interested in looking at the quantification of the Goldschmidt classification. So Goldschmidt, of course, many of you are probably familiar with. He was a Norwegian geochemist in the early 20th century. And he came up with this classification scheme that is shown on the periodic table there of how the elements tend to behave in the natural world and what kind of reservoirs they tend to go into. So this is something that Goldschmidt himself actually published in 1939. And it's such a useful tool, it's such a useful classification scheme that we geologists have been using it ever since. And the categories that he came up with are, if you tend to find an element in just normal run-of-the-mill silicate rock-forming minerals, then we refer to that element as lithophile. If it tends to occur in the metallic state, if it tends to stay in native metals, then we refer to it as siderophile. If it tends to occur with sulfur in the form of sulfide minerals, then we refer to it as chalcophile. And if it doesn't tend to go into solids at all, if it tends to just stay in the oceans or atmosphere, then we refer to it as atmophile. So here's just an example, and of course, you don't have to look across all of these numbers, but here's an example of how we can quantify all of these correlations. So in each row and each column here, I'm listing some common mineral-forming elements. And the correlation between any two of them, you just go to the diagram, for example, magnesium and oxygen would be right here. And the value, and what value is it that I'm plotting right here? What does this 32.8 represent? What it is it's the logarithm of the p-value that results from the statistical test between the correlation of those two particular elements. Okay, and then I've got them signed so that positive correlation values are given in green, and negative ones, in other words, anti-correlations, where those elements do not like to occur together, are shown in red. And you notice a couple of interesting things here. If you choose a column, for example, take this column for oxygen, and notice, well, first of all, there's a ridiculously strong correlation between oxygen and hydrogen, right? And that makes a lot of sense. Those are hydrous minerals. But then as you go down the list, you get somewhat weaker correlations, but there are some positive correlations here between sodium, magnesium, aluminum. Okay, again, that all makes sense. Those are all lithophile metals. They tend to occur in oxide and silicate minerals, so they're going to be associated with oxygen. Then we get down here, it's very strongly anti-correlated with sulfur. And the reason for that is that the oxides and silicates are a huge mineral group. Sulfides are a huge mineral group. And there's not much overlap between them. There are the sulfate minerals that have both sulfur and oxygen, but their numbers are much less than the numbers of either the silicates or the sulfides. And so you get these correlations popping out at you. So now what can we do with all of these correlations? Okay, I mean, we're kind of already aware of some of them, certainly. But if you think about this correlation with oxygen, this is, in a sense, we could use this as a quantitative measure of the so-called lithophilicity. I guess I'm making up that word. That's a word that did not exist beforehand, but I'm calling it the lithophilicity of that particular element. Whereas if you look at the silicon or the sulfur columns, once again, we have quantitative measures. Silicon could also be a measure of lithophilicity. And then the correlation with sulfur could be a measure of the so-called chalcophilicity. How strong is the chalcophile behavior of that particular element? And could we potentially use that to, find new avenues and new reservoirs of that particular element? Well, this seems to work if you look at the stretches of patterns here. So all of these elements that are in the top rows here are indeed positively correlated with oxygen and silicon, but they are negatively correlated with sulfur. So that would certainly seem to indicate that they are strong lithophile elements. A few of the elements down here, nickel, copper, zinc, are positively correlated with sulfur, but negatively correlated with other elements. So they, of course, would be termed chalcophile. Now, if you take all of these values and plot them out on the same diagram, so here I'm showing the chalcophile tendency on the vertical axis and the lithophile tendency on the horizontal axis. And what you find is that there's a really striking correlation between the two. And this is something that I presented just last year to the International Mineralogical Association. I'm showing here both the red and blue data points. The red is the correlation with oxygen, the blue is the correlation with silicon. And you can probably see the correlation is somewhat better when you use oxygen. That seems to be the one to go with. So there's this strong linear anti-correlation between the measures of lithophile behavior versus the measure of chalcophile behavior. And you can develop essentially a spectrum of all of the elements that plot on this diagram, where in particular we're going to use the oxygen values because you can see it's R squared, its correlation value is much higher than it is for silicon. So elements like silver, which I used as an example in the beginning, actually turns out to be, by this measure, is the strongest chalcophile element. It loves to occur as sulfides and essentially never occurs as an oxide. And then other chalcophile elements also plot along this diagram. Copper, antimony, lead, okay, all of those things plot on the chalcophile side of the spectrum. And then over here, we've got lithophile elements like silicon, calcium, aluminum, all of those plot on this side of the diagram. So here is sort of the first quantitative measure of all of these behaviors. And it starts to correlate, minerals that have these elements, and what we see in the natural world starts making even more sense. So we have lithophilicity downward in that direction, and then chalcophilicity in that direction. So I would propose that this is a really interesting way to quantify these behaviors, and I can envision geochemists in the future, when measuring the partition of elements, looking at crystallization behavior, looking at the ore grades of different ore deposits. I can picture them using, these quantitative measures of the chalcophilicity and lithophilicity. Here's how it looks when you plot it out on the periodic table. You get, very much the same kinds of trends, but with more information, as with the Goldschmidt classification. So the elements shown in red here are the ones that tended to be lithophile in behavior. Yellow is chalcophile behavior, and then green is showing just that there was not a strong enough correlation. It didn't particularly fall under the lithophile or chalcophile categories. This block of elements here, this entire block showed up as chalcophile in all of these analyses. And if you compare this to the actual Goldschmidt classification and look at that same box, there they all are. The box containing all of those elements was actually classified as being chalcophile in behavior, but now we can see it in more detail. So, we get a very strong correlation with what we previously knew, but now with a lot more information. I am going to I haven't gotten to mineral evolution yet. So in the interest of time, this is another really fascinating correlation, but I'm actually going to skip over it. And if you're interested in hearing about it, I'm happy to talk to you later. But the upshot is that certain elements tend to associate strongly with hydrogen and oxygen in minerals. They tend to be, in other words, they tend to involve water, and other elements do not. And that trend, by the way, is something that's totally new. It does not correlate with the Goldschmidt classification or with any other measure that we have looked at. So that's kind of a new idea in mineralogy that we've found using these trends. So let me wrap up here by talking about a particular project that I did recently in mineral evolution. And mineral evolution is the study of how mineral distributions have changed over time. Okay, so this time we're throwing in a time dimension. Sorry about that. So, of course, geologists have been looking at the development of minerals through time for quite some time. Sorry, my voice is getting a little bit dry. If you give me just a moment, I think I'm going to grab some water and then I'll be right back.
Take your time, Daniel.
So what was that?
Take your time.
Okay, thanks. I'm sorry for the delay there. So on your screen there is a histogram distribution of the ages of zircons. And of course, people who work in geochronology have been using zircons for a long time to date some of the oldest materials that we find on Earth. And it turns out if you plot up a histogram of all of these ages of all of these different zircon grains, you get this very nice multimodal distribution where there are peaks in the production of zircons at particular periods of geologic time. And those peaks in zircon production correspond very, very nicely with the appearance of supercontinents. So this is the sequence of supercontinents that we've seen on the planet: Kennerland, Columbia, Rodinia. Panotia was a somewhat smaller one, and then of course Pangaea, which started breaking up, some 60 to 70 million years ago. So we know that mineral formation, at least, these kind of primary igneous minerals, is very largely driven by tectonics, by these tectonic cycles. So I wanted to know Well, we can do this with this particular mineral, zircon, but can we do it with other minerals, and can we do it with entire mineral systems and look at how that chemistry systematically changes over time? And in particular, I was really interested to see what the effect of oxidation was, because we know one of the major events in Earth's history was the Great Oxidation Event, where oxygen entered the atmosphere for the first time. So I picked out a redox-sensitive element. The element that I used for this study was manganese. It's a great one to use because it's a fairly common element. It's actually the 12th most abundant element in the Earth's crust. So it appears in a lot of minerals. It appears in several hundred different mineral species. So that means we have a lot of data to draw from our database. And it's also very redox sensitive, and it occurs in 3 different oxidation states. It can be +2, +3, or +4. And in this graph of element abundance here, it sits among these most common dozen or so rock-forming elements. And of course, the oxidation state of the manganese is going to heavily depend on the oxygen fugacity, the amount of oxygen that is in the surrounding environment. So for example, at very low oxygen fugacity, you get +2 manganese, sometimes mixed with +3 manganese in a mineral like santaroite. If you go upwards from there, then you get all Mn3+ in minerals like purpurite that also occur in igneous rocks. And if you go all the way to higher oxygen fugacities, then you get a dominance of Mn4+. And so that's things like ramsdolite, the very common pyrolusite, other things that tend to form manganese ores. So do the proportions of all of these different minerals change over geologic history? Is the main thing that I wanted to know. So first, we can just plot up the age distribution. We can form an age histogram, just like geochronologists have done with zircon as a mineral species. And when you plot this up for manganese minerals, which is the first thing that I did with the manganese mineral data set, what you find is that indeed there are spikes in mineralization that seem to surround the appearance of the supercontinents, exactly the same supercontinents that was forming zircons. So again, we see this strong effect of tectonics. The mineralization seems to coincide really well in most cases with supercontinent formation. There is a bit of a weird effect at Rodinia here. We get a lot of mineralization right at the beginning of Rodinia and right at the end of Rodinia. And we don't completely understand the reasons for that yet, but that's another thing to explore. If we take all of these minerals and we put them into time bins and we average the oxidation state of the manganese, then you can develop a graph that looks like this. And this is something that I just published in Nature Communications last year. And you can see that early on, about 1 billion years ago, we see lower values of the manganese oxidation state, values that are much closer to 2. But then as we get into the Phanerozoic, starting about 600 million years, that average oxidation state starts to go up. It fluctuates some. It reaches a maximum right here at around 250 million years. It does some fluctuating, and then it levels out to this value right here. Okay, so it's showing us that indeed there is an effect of oxidation here on manganese that we can track through time that is a reliable trend because it's larger than the error bars. It's showing us that there's a real effect here. So I overlaid this. This is what it looks like when we overlay that manganese oxidation data over reconstructions of atmospheric oxygen. So of course, people like Heinrich Holland, and Canfield at Oxford, I believe. Many people have been using these various different geochemical proxies to reconstruct what the atmospheric content of the oxygen content of the atmosphere was. And so here are some of those reconstructions that I'm showing right here. And notice that around 300 million years, there is a spike, there's a local maximum in oxygen concentration, and it's followed just a short time later by a major spike in the oxidation of manganese minerals. Okay, so this turns out to be a very real correlation. If we shift all of these values over by about 66 million years, then the trends line up perfectly. And by the way, we didn't just do this visually, we did a statistical test to see if there was a direct correlation between the atmospheric oxygen and the manganese chemistry. And there was a very strong correlation. And in fact, the period of the oscillation of the manganese came out to be, if you look at the period between the highs and the lows, turns out to cycle over a 35 million year period. In the oxygen reconstructions, the period turns out to be 35.7, so very, very close. So there's a very tight connection here to be found. So what we think this means is that oxygen rose in the atmosphere. It was being produced by microorganisms that were conducting photosynthesis. It was pumping oxygen into the oceans and the atmosphere. And then there's somewhat of a time lag as that oxygen slowly works its way through fluids, through processes like subduction, works its way into the Earth's crust and began oxidizing all of those manganese minerals. So we have cyanobacteria, building up photosynthetic oxygen in the oceans. That then leaks into the atmosphere. Oxygen builds up in the atmosphere. And then very slowly over time, that oxygen infiltrates the Earth's crust. And at least starting at the surface of the Earth and then moving downward, we begin oxidizing all of those manganese minerals, and we get that signal of manganese oxidation. And there is apparently, by the way, a time lag. All of these processes averaged together seem to have a time lag of 66 million years to have this effect, but the effect is definitely there. You reliably see the manganese oxidation moving in the same direction as what atmospheric oxygen was doing. So I think this is a really powerful new technique to look at the changing geochemistry of various Earth reservoirs over a spanning most of Earth's history. And I'm going to wrap up just kind of giving you, yes.
5 more minutes? Possible?
Yeah, I'll actually, this is like the last slide. I just wanted to briefly give you my philosophy moving forward in doing these studies. Obviously geologists have been analyzing samples and doing experiments for a long time. And I think that these new, so-called big data studies have a really large amount of information to contribute to this. But of course, we can't just do that alone. We need this in combination with the techniques that we're already using. So in my view, we do lab experiments. That gives us things like the thermodynamics of different mineral phases. It tells us about the structures. It tells us about the rates at which minerals react in different environments. Analysis of natural samples tells us about past geochemical processes. It tells us about conditions that existed at a particular place on Earth at a particular time. And then I think that big data studies, they are contributing global scale trends. They're telling us broad processes that were taking place across a lot of the Earth across a very long period of time. And when we combine all of this information, it tells us things about the prevalence of different geochemical processes at different periods in Earth's history. It tells us about the evolution of the planet, but of course, we have to correlate that with what we already know about the behavior of minerals. So I think the three of them together are going to reveal a lot of new things about Earth's history that we didn't know before. It's already happening. Myself and several of my collaborators have already published things along these lines, and I think this is a really exciting new frontier to combine with what we already know and give us the big picture. So I'll just wrap up there and put some conclusions up there. We can use statistical distributions of minerals to allow us to predict new minerals and actually find them. We can use network relationships in order to predict where minerals will occur at specific points on Earth and learn things about geologic history in those particular locations. And then we can also use global data sets, as I just showed, to kind of summarize major geochemical changes across Earth's history. And I think that's going to be a really exciting new frontier. So I will wrap it up there. Thanks so much. That ran a few minutes longer than I was intending, but I certainly hope that there's time for some questions.
Thank you, Daniel. I suggest we start with questions from the room first. And people online, if you have a question, use the hand gesture that will enable us to set an order to give you time to ask your question. And for those in the room, if you have questions, speak louder so Daniel might be able to hear us. So any questions? Yes? So thank you very much. I was wondering whether for the manganese data sets, you used only 1 billion year record, right? You did not use very, very old data, like 3 billion years. And I was wondering, what is the reason? Is that there are no data, or not enough data, or no oxidized data?
Oh, yeah, that's a good question, right? So I showed it back to about to 1 billion years, right? But of course, we've got, we have these ages going back to 3.5 billion years. Yeah, that's a great question. I sort of glossed over that. We do have data that goes further back in time, but it turns out once you go past that billion-year mark, the number of mineral occurrences that you find drops off significantly. And so as a result of that, yes, we do have data, but when you're trying, for example, to plot up that average oxidation state, there are fairly large error bars on that oxidation state. And what we found is that we just past 1 billion years, we just didn't have enough data to make statistically robust conclusions. So yes, there is data, and we think that we see some trends. But in terms of the manganese mineral data set, there was not enough to really allow us to do a statistically rigorous study. But we do think actually that there are other mineral systems, such as iron minerals, is a big one. There's over 1,000 iron mineral species. And one of my graduate students has undertaken a study of how the iron oxidation changes over time. And there we actually do have data going back, 2 billion, 3 billion years that we can take a look at, and we see some interesting trends.
Yeah, thank you very much. And it's a somewhat related point. Where do you put the cursor to examine the diluted elements? For instance, if I have manganese in a calcite, for instance, or manganese in the carbonate or whatever.
Oh, do you mean like what minerals are we using?
Yeah, do you use it on the data when you have a very low concentration of the element in the mineral?
Yeah, great question. For this particular study, there are so many minerals that contain manganese as a major element that we simply used those. So in other words, to be included in this study, it has to be a mineral that actually contains Mn in the nominal chemical formula of the mineral. And it turns out there's in the neighborhood of 500 of those, 500 to 600 manganese minerals. And that was plenty enough to do an analysis with. But there are other studies where we are looking at concentrations of minor or trace elements that are occurring in other minerals. So in this study, we did not use manganese, occurring as a minor element in other minerals. But for other studies, we're taking advantage of that.
Other questions? Online? Oh, Emmanuel? Go ahead.
So you mentioned an estimate of 9,000 mineral species on Earth. Is there a comparable estimate for the number of mineral species in meteorites? Currently,
for the number that occur in meteorites?
Yes, the number of mineral species in meteorites. Currently, I think 435 have been compiled. Others are discovered in
That's a great question. I have not seen a specific prediction for the number that are in meteorites. I've seen it for Earth though, and you get this 9,000 number. I've also seen it for, I believe they've done it for Mars, and they predict a few hundred total mineral species on Mars, but I've not seen it for meteorites, and that's a good question because some of the, some percentage of the new mineral species that we find every year do seem to consistently come from meteorites. So yeah, that's a good question. I don't know the answer though. I've not seen a specific prediction for that.
Any other question? Yes.
So I will try to be clear. I was wondering from this big data set, can we learn in terms of thermodynamics, of formation or evolution of rocks when we got alteration, and like when we are looking on rocks, many times we have problem of there is some minerals which are together and you don't know really if they are formed in the meantime or if they are formed due to the evolution of the rocks to prevent free alteration, metamorphism, I don't know, something like that. And what could we learn when we look at the rocks?
Sorry, I didn't catch all of that. Were you referring to mechanisms of formation?
I was just wondering what can we learn in terms of thermodynamics from each huge data set, and when we look at the rocks and like sometimes you don't understand if this mineral is formed in the meantime of the rocks or later on due to alteration or things like that, and what can we learn in terms of thermodynamics and environmental conditions.
Oh, I see. Yes, so that is actually something that they are actively working on in the database right now. So one of the problems, of course, which I think you were getting at in your question, is that sometimes you form a deposit of primary minerals, but then millions of years later you get alteration or oxidation or something happens, and it produces new secondary minerals. But of course, those secondary minerals don't necessarily have the same age as the primary minerals. Yeah, and that can definitely goof up, when you try to extrapolate that to the thermodynamics. So yes, what they're working on right now is going through each locality and dividing them up by the paragenetic mode. They're actually adding paragenetic modes to each mineral species. And if a mineral species occurs by a different paragenetic mode at a particular location than other minerals do, then what we do is we separate those in the database and we consider the possibility that, okay, maybe this group of minerals that formed it through this mechanism have a particular age, and perhaps these other minerals that that are found at the same deposit, but they're formed through a different mechanism, they may have a different age. So we're trying to split those up now by using the paragenetic mode as a parameter. And Bob Hazen actually just recently published, he and Shauna published an analysis just last year of all the possible paragenetic modes and how all the mineral species fit into them. So that's in the process of being added to the database right now, and we're hoping that will tease apart some of the issues that you just talked about.
Thank you. A last question, maybe? Online? No? Okay, let's thank Daniel one last time. Thank you.